Okay, 10.2, parabolas. Now, parabolas are kind of wacky because we've spent some time, and I know you've spent a lot of time in previous classes, graphing parabolas, right? Deciding if they open up or down, which way they've been shifted, where their vertex is, where the axis of symmetry is, all kinds of stuff. But we also need to concentrate on parabolas that open to the left or to the right. So this gives us a way to do that. And it gives us a way to kind of visualize and sketch the shape of a parabola without fully knowing every point on the curve. Okay, so getting an idea of what the parabola looks like without playing pick a point for too many points and stuff like that. And then also concentrating on parabolas that open left or right, which we haven't really had much experience with. So as a locus, a parabola is a locus of points that are equidistant from two things. We have what's called a directrix, so this is going to be a line, and then we also have a point that's not on the line, and that's called the focus. Right here. And if we look at the locus of points that are equidistant from these two things, what we get is a parabola. So let's look at some of the points that would qualify. We could obviously go perpendicular to our directrix from the focus, and halfway in between those 2 points would be a point, right? And that's actually going to be a special point. That is going to be the vertex of our parabola. So we'll label that. And let's think about some more. If I come kind of over in this direction a little bit and think about a point that is going to be equidistant. Okay, let me go ahead and put a dash line in here from both the focus and the directrix. Imagine that those distances are the same. Then this point here would be on my parabola. How about another point up here? This distance and this distance to the directrix are going to be equidistant, so this point is on our parabola. And keep in mind, when you are measuring a distance to a line, you want to make sure that the distance is perpendicular. Okay, so I've tried to come in right at a 90-degree angle. But you're going to get all these points on both sides. We can go to this direction too, such that if you were to sketch the distance between the focus and the directrix, they would all be equidistant from both of those things. Okay, I'm going to pick one special point over here. I'm going to call him x comma y, and these distances are going to be the same. I'm going to call the distance to the focus is d1, and the distance to the directrix is d2. So every point has this in common, that d1 is going to equal d2. Anything else I want to put on here? I did mention the axis of symmetry. I'm going to draw it as a solid line. It will pass through both the focus and the vertex, and it will be perpendicular to the directrix. And this is going to be our axis of symmetry, sometimes just called the axis. Okay. So use the definition to write the equation for a parabola with a focus at 2, 4 and a directrix at y equals 2. Okay. So what we're going to do is we're going to make sure that these two distances are the same. And my d1, I'm going to call the distance between, and I'm going to name this point so we can talk about it a little bit easier. I'm going to name this point P. D1 will be the distance between the point and the focus. And I need to make sure that that's equal to D2, where D2 is the distance between point P and the directrix. I'll just call it with a capital D. Okay. Well, we're going to use the distance formula, right? The distance between 2 points. Let's make my focus point a little bit darker. There you go. The distance formula gives us the length of a segment between 2 points. So if I'm using this point at x comma y, and then my focus is given in this problem. Okay, so I'm going to do the square root of x coordinate minus x coordinate. So I'm doing, my point is at x comma y, and then my focus is at 2, 4. So it'll be x minus 2 squared plus y minus 4 squared. A quick sketch of this. My focus is at 2, 4. Let's say that's right here. And my directrix is a horizontal line at y equals 2. So it's right here. I know that this parabola opens up because the vertex will be halfway in between the focus and the directrix, and it's going to open around the focus. That's always the case where the focus is kind of in the interior of the parabola. So it looks something like this. Okay. When I want to measure the distance between P and D, so remember my point P is any random point, and if I want to measure a distance to a line now instead of a point, what is the same about point P and D? They have the same what? They have the same x coordinate, okay, because the directrix really has every x coordinate. So I only really need to worry about the difference in the y's. I only need to know how far this point is off of whatever that y value is. Well, this is a horizontal line at 2. So the distance between my point P and the directrix is just going to be the square root. And again, the x coordinates can be the same because we're going to go right down perpendicular. And so I only have to worry about the y's. So it's just going to be y minus 2 squared. Okay, so this is how we're going to set this up. We can go ahead and square both sides. Let's just get rid of those square roots. So we have x minus 2 squared plus y minus 4 squared is equal to y minus 2 squared. Okay. I'm going to go ahead and rewrite this, but what I want to do is I'm going to leave the x squared stuff in factored form, but I'm going to go ahead and FOIL out the y squared stuff because I'm going to be able to combine some like terms. So let's leave x minus 2 squared. I'm going to FOIL out this guy, so that'll be y squared minus 8y plus 16. And on the right, same kind of thing, I'm going to have y squared minus 4y plus 4. And then what I'm going to do is let's just put all of the y stuff on the right and leave the x stuff on the left. So I'm going to leave x minus 2 squared. And when I subtract y squared, they're actually going to cancel. Okay, so we're only going to have this negative 8y plus 16 to move. So I'm going to go ahead and add 8y to both sides and subtract 16. Okay. And something that's going to be handy is I'm going to go ahead and factor a 4 out of both terms on the right. This becomes y minus 3. And we want to notice something. Remember that we said our vertex is this red dot over here. Our vertex is going to be halfway in between the focus and the directrix. Well, if our focus was at 2, 4 and our directrix was at y equals 2, then our vertex is just going to be the average of those y's. Our vertex is going to be at 2, 3, which is halfway in between 4 and 2. And look at our equation now. Does it make sense that our vertex is at 2, 3? Okay, and we can see that here in the equation. So this is going to be kind of standard form of a parabola, and we're going to talk about this a little bit more, how to get this. That this is a useful form because we can look at it and see what the vertex of the parabola is going to equal. Okay, let's do this again, but we're going to do it with a parabola that opens left or right. So I'm going to do a quick sketch again. My focus is at negative 5, 5, over here somewhere. And the directrix is at x equals 7. That's way over here. X equals is a vertical line. Okay. Remember that the vertex will be halfway in between the focus and the directrix. So right around here. And we're going to open around the focus. Okay, so we can get a pretty good idea of what this parabola looks like just by having the focus and the directrix. Okay, but let's get an equation. So same kind of thing, the distance d1 between my point and my focus has to be equal to d2, which is going to be the distance between the point and the directrix. So let me pick a rando. Here's point P. It has coordinates of x and y, and we're going to compare. Oops, my directrix isn't quite long enough. There we go. The distance of this perpendicular distance is, and look how, and we can tell that the shape of the parabola is going to have to do with this distance, right? Look, notice how mine looks way off, right? My focus looks way closer to P than the directrix is. So let me fix this. My parabola needs to open up more. It needs to have a little bit wider of a shape so that this looks more, and they do not have to be drawn to scale. If you told me the distances were the same and it didn't look like it, as long as you told me it was true, I would believe you, okay? But if I want to make this a little bit more accurate, I'm going to make it a little bit wider of a parabola. That still looks fishy. But now maybe this looks a little bit better. Oops, make sure to go perpendicular. Here's my point P now on the curve, and I'm comparing the distance to the directrix to the distance to the focus. That looks a little bit better. Throw a tick mark on there, and maybe you'll believe me that those are supposed to be congruent. Okay, anywho, back to my equation over here. The distance between the point P and the focus, remember that's going to be distance formula again. So between x and y and negative 5, 5. So we're going to have the square root of x plus 5 squared plus y minus 5 squared. And then the distance to the directrix. This time my directrix is a vertical line, which means I can have any y coordinate I want. The same as my point is perfect, okay? And then I only have to worry about the distance between these x values. So really this is going to equal the square root, and the distance between the x's will be x minus, and my directrix is at 7, so x minus 7 squared. I'm going to do the same thing that we did above. I'm going to square both sides, cancel the square roots, so this will be x plus 5 squared plus y minus 5 squared equals x minus 7 squared. This time I have two squares with an x in them, so I'm going to go ahead and FOIL those out, and I'll leave the y minus 5 clumps together. So this will be x squared plus 10x plus 25. Leave the y stuff as it is. And on the right we'll have x squared minus 14x. Spacing out, sorry, plus 49. I'm going to move all the x stuff to the right, so when I do that, the x squareds are going to cancel. And we'll isolate this x minus 5 squared. I'm going to subtract 10x, so that'll be negative 24x. And I'm going to subtract 25, so that's going to give me positive 24. I can actually factor 24 out of both of those terms. And I want to take the negative with it, negative 24, and make this x minus 1. Okay. So, two things to look at here. My vertex is going to be at the point 1, 5. And hopefully that makes sense to be halfway between the focus and the directrix. It's 6 units from each. And this negative sign, my parabola opens towards the negative side. Okay, if this were a positive 24, the parabola would open to the right. Okay, so this is going to give us a couple of pieces. Okay, so what I'm going to do is I'm going to look at the two equations that we just determined and see if we can find some common information. So for the first one, it was x minus 2 squared is equal to 4 times y minus 3, and that's after we factored the left hand, or the right hand side. And for the second one, we got y minus 5 squared is equal to negative 24 x minus 1. And we said that this is a good form because you can see the vertex. So the vertex for the second one was at 1, 5, and the vertex for the first one was at 2, 3. The other thing that we can point out is which direction these open. The first one opened up, and the second one opened to the left. And what this is going to stem from is based on whether this piece is positive or negative that we factor out of the term that doesn't have the squared, right? On the right hand side, in this case it was the y, and in this case it was the x. But when we factored a term out, this 4 was positive, and we see that our parabola opens up, and you can see that it does, and the second one opens to the left. If we had factored, if the y was singular, right, it's not squared, and we had factored out a negative, it would open down. And then this one, if it had been a positive number that we factored out, then it would have opened to the right. So that's something handy that we can tell from looking at the equation. Okay, and what I mentioned before is that a parabola will start at the vertex and it opens around the focus and away from the directrix. So if you know where the focus and directrix are, you can sketch a parabola. And if they're far apart, like these ones, it's going to be a wide parabola, okay? Because I needed to make those segments a little bit more equal, so I had to make my parabola a little bit wider. This one, this doesn't look terrible, but you can see that the focus and the directrix are closer together, and the parabola is going to be a little bit skinnier. So it helps you with the shape as well. Now, let's talk about this p-value. The piece that's in front of the piece that's on the right-hand side, or the piece that doesn't have the squared, right, is, in both of these cases, is 4 times something, and that is going to be we're going to call it a p-value. I don't know why, I don't know where the p-value comes from, but in this case, that would give us a p-value of 1, and in the second one, the p-value would be -6. So we know that if it's a y squared, it's a parabola that's going to open to the left or to the right. And if your p-value is negative, it opens to the left. If your p-value is positive, it opens to the right. Okay. If it's a parabola that has its x squared, these are the ones that we've been doing for years, right? It's either going to open up or it's going to open down. And based on your p-value, that will tell you which one it is. The other thing the p-value tells you is it's going to give you the distance between the vertex and both the focus and the directrix. So we know that the vertex is equidistant from both, okay? And in this case, because I factored that -24 out, that's 4 times 6. Notice that the vertex is 6 units from the directrix, which is at 7, and 6 units from the focus, which is at -5. Okay, same kind of thing for the first one. I just said our p-value is 1, and if we look at the graph, our vertex and our focus were 1 unit apart, from 2 to 3 to 2 to 4, and then same to the directrix. The vertex is 1 unit above the directrix. Okay, so we get all kinds of information here. So in the general forms of these, if we have a vertical axis, which means the parabola will open up or down, typically you will see all the x stuff is on the left, and then you complete the square if you need to and get that as a binomial in terms of x that's squared. And then on the right, you put everything else, and you want to factor a 4p out because that's going to give you both the y coordinate of the vertex and some more information, right? If it's a horizontal axis, which means it opens left or right, it will flip-flop these two pieces. So the y stuff is the piece that will be squared, so y minus k squared, and that will equal 4 times p times the x stuff. All right, so here's another way to write the equation. This time we're given the vertex and the focus. Okay, so let's think about this. I'm going to draw a quick mini sketch just to see which way this thing is going. The vertex is at 3, 2, and the focus is at 1, 2. So remember, my vertex is going to be the start of my parabola, and it's going to open around the focus. So this thing has a horizontal axis, which is going to means it's going to be in this form. And it opens to the left, which means my p-value is going to be negative. Well, what is the distance between the focus and the directrix? Go ahead and put that into the Edpuzzle. They're 2 units apart, right? So our p-value is going to be negative 2. And then the only other thing I need to write the equation is the vertex and to plug that in. So this is going to be y minus, this is going to be the y-coordinate of the vertex is 2. 4 times our p-value is going to be negative 8. And then x minus the x-coordinate of the vertex, which is 3. So there is the equation of that parabola. All right. Another piece of a parabola that can be discussed is what's called the latus rectum. So let me sketch a parabola. This is kind of a wide opening parabola, so maybe I'll make my focus fairly good distance away. Here's the directrix, vertex. So what we do if we draw a line that's parallel to the directrix, but that passes through the focus, which is in this definitions, means that it's going to be perpendicular to the major axis. My major axis, remember, goes through the focus and the vertex. And it goes from one point of the parabola to the other. That is what's called the latus rectum. And what's nice about this point, I know that the distance from the focus to the directrix, because the latus rectum is parallel to the directrix, these segments are going to be congruent. This distance is equivalent to this distance, right? Because it's basically a rectangle that's created, and opposite sides are going to be congruent. And then also what that's going to be equal to, because because this point is just any point on the curve, it has to be equidistant from the directrix and the focus. So that's also going to equal this length. Okay, so the length of the latus rectum, if I go all the way across, right, from one point to the other, it's going to be 2 times the length of from the focus to the directrix. Now, we said our p-value is, let me highlight, this distance is p. So the distance from the focus to the directrix is going to be 2 times that. So each of these is 2p. And then the length of the latus rectum is going to be twice that. So it's 2 times p, or has a length of 4p. So let's see if this is going to help us. So this actually helps us get a little bit better of an idea of the shape of our curve, of how wide we need to make it. This will help me for sure. Okay, so what we're going to do for these 3 parabolas, we're going to find some information about them and then sketch them. Okay, so for the first one, x squared equals 6 times y. I've got the x stuff on one side, the y stuff on the other. The only other thing I would want to do to this is just factor a 4 out of that 6. So if I divide 6 by 4, that would simplify. 6 divided by 4 simplifies to 3 halves. So 4 times 3 halves is the same thing. I want it like that because that gives me my p-value. Because this has an x squared, are we going to have a vertical or a horizontal axis? And number 2, because the p is positive, that means we're going to open where? What? Up, right, left, or down? So hopefully you said up, okay? x squared means it's vertical, and a positive p means that it's going to open up. Also, because there's nothing subtracted from x or y, that means our vertex is going to be at the origin. And we can get our focus and our directrix from this information. So our vertex is at 0, 0. Our p-value is 3/2, which means the focus is going to be 1.5 units above, and the directrix will be 1.5 units below. And if I double that length, if I double p, I get 3, which means the lattice rectum will have a segment that reaches 3 units on either side of that focus. So that gives me some guidelines to help me sketch the parabola a little bit better. Okay, and that's enough information. That's a pretty good parabola in terms of what we need to know. You can always plug this into Desmos to double check your work. We're going to have to pause though now and go to the next video and finish the last 2. Okay, we have 2 more parabolas to graph and analyze. So here's what we're looking at for B. I've got y stuff that's being squared, so I'm going to complete the square for y on the left and then move everything else to the right. So on the left hand side, we've got this y squared minus 2y. I'm going to complete the square by taking half of 2 and squaring it, so I'm going to add 1 to that. And then on the right, we've got 8x minus 1, and then I'm going to add 1 to that. So I've just forced the left-hand side to factor to be y minus 1 squared, and on the right, we're just going to have 8x. So what I like to do for the p is I'm going to factor a 4 out of that 8. So this would be 4 times 2. And that tells us that our p-value is 2. Okay, because this is a problem where the y is squared, it is going to open to the left or to the right. And because the p-value is positive, it's going to open to the right. And then also we can figure out the vertex from this information. So the vertex is going to be, there's nothing being subtracted from x, and there's a 1 being subtracted from y. So our vertex will be at the point 0, 1. And then I like to kind of graph while I figure out where the other pieces are. So I'll list them, but the vertex is at 0, 1. And because this thing opens to the right and the p-value is 2, that means our focus is going to be 2 units to the right of our vertex. So our focus, we're going to add 2 units to the x coordinate. So that will be at 2, 1. And then our directrix will be 2 units behind the vertex. So the parabola opens away from the directrix. So my directrix, let's use a capital G for that. Directrix will be the vertical line at x equals -2. Okay, I like to get a couple more points, and these are the ones on the lattice rectum to be able to, identify the shape. Because these points are a little bit further apart than the last ones, it means my parabola would open a little bit wider. But if I actually get some points on here, that's going to help me more. So the distance from the focus to the directrix is 4 units. So that's how far I'm going to go away from the focus to put points on the lattice rectum. So I'm going to go 4 units up and 4 units down. And that'll help the shape of my parabola. And it should look something like this. Okay. One more of these. Normally I wouldn't necessarily move the y squared. It doesn't necessarily have to be on the left, but because it's negative, I do want to move it to the other side. So I am going to add y squared to both sides and then subtract the x. So I'm just going to flip-flop those two, the locations. We don't need to complete the square for y in this case, okay, because there's no blank y term, no linear y term. So I'm just going to concentrate on the right, and I would probably just reorder those. This is the same as -x plus 3, and so what I would want to do is actually factor a -1 out of that and make this x minus 3. Just because it's going to be more clear in this form what the vertex is and what the p-value is. So remember, this is still 4 times something. And to be able to make that back into -1, I would want to multiply by -1/4. So that's equivalent just to that -1 in front, and this is still times the x minus 3. So my vertex is going to be at 3, 0. The p-value is equal to -1/4. And because the y term is squared and not the x, this will open left or right. And a p-value that's negative means it will open to the left. What else do I need? I guess I'll just graph next. So the vertex is at 3, 0. The focus is going to be very close to that, right? Yeah, it's just over 1/4 of a unit. And then my directrix would be back 1/4. Okay, so here's an example of where these things are really close together. Whoa, what happened to my leg? Got even wackier than normal. Okay, so the distance between the focus and the directrix is only 1/2 a unit. So when I plot the points for my latus rectum, theirs are going to be only 1/2 a point away. So this is going to be very skinny. If this were a more technical graph, I might get some more points to put on there, but this is fine for now. All right, let me know if you have questions about any of that, and I will see you back in Zoom.